Okay, hello everyone, this is Fluid Machinery, and this lecture is about positive displacement pumps. So when we started this whole course, I said that there are two huge families of pumps, one of them being the so-called turbo pumps. So they have impellers, like the blades of this wind turbine, or the blades of this axial fan, or the impeller of this pump. Their operation is described by Euler's pump equation, and they are described by velocity triangles. However, there's another big family, which is called positive displacement pumps. There are two main types of these pumps, one of them being the piston pumps. Okay, for example, this machine here. So clearly it has a piston that has an alternating motion, so it moves back and forth. Okay, and this is how it pumps. And the other one is the rotary pumps. One example is the gear pump, in which you have a gear which is rotating, and then the fluid that is entrapped in this area is simply pushed from the suction side to the pressure side. So today we are going to deal with these pumps. So let's start by developing some equations for the flow rate. So if you have a look at this gear pump, so what I'm saying now is valid for all of the pumps, but I will explain it on a gear pump. So if you have a look at this gear pump, clearly the quicker it rotates, the more fluid it conveys. So the theoretical flow rate is the revolution number given in rotations per minute. So RPM per minute. Okay, times this thing here, which is called geometric displacement. Usually we say that it is cubic centimeter or liter, so it's a volume, but in the reality is the volume per revolutions. Okay, and hence if you have something like volume per revolutions, then at the end of the day the dimension of this thing will be volume divided by time, so cubic centimeters per minute. Okay, so RPM is simply rotations per minute. So what you need to do is you need to multiply this geometric displacement by the revolution number. So the higher the revolution number will be, the higher the flow rate will be. Now this geometric displacement is nothing else but the flow rate of one shaft revolution at zero pressure difference. So what you do is you make one full revolution at the shaft of the machine, and then you simply measure how much fluid it conveyed. Okay. Now it's important to have it at zero pressure difference because the real flow rate is smaller than this. There is a new factor called volumetric efficiency. It's not really new. This is something we've already done with turbo pumps. This is always have something to do with leakage. Leakage. Sorry for the terrible handwriting. So the leakage occurs here and also at the two ends of the gear because the outlet pressure is high, the inlet pressure is low, and here at the tip of the gear there is a small gap because you don't want the two metal surfaces, so the inner section of the house and the outer, the head of the gear, you don't want them to be in contact because then you will have galling and all kinds of problems. So there's a small gap, and if there is a gap and there is a pressure difference, then there will be a leakage flow, a backflow. Now this backflow is a leakage, and the higher the pressure difference is, the higher the leakage is. And this volumetric efficiency is simply the ratio of the true flow rate and the theoretical flow rate. Okay, the higher the pressure difference is, the higher the leakage is, so the lower the volumetric efficiency will be. Okay, so this is our equation for the flow rate, volumetric efficiency times revolution number times geometric displacement. Again, this geometric displacement is simply the size of the machine. Now we need to develop some equations for pressure difference. But before we do that, we'll split into two parts. We'll speak both of pumps and motors. It's very interesting that many of these pumps can be used as motors, as follows. So if you think of a pump, what happens there? You have a shaft. You're rotating the shaft, for example, with an electric motor. So you're rotating your shaft, and your pump will deliver flow rate and pressure difference, so you will get hydraulic power. But for example, if you think of a gear pump, you could use it the other way around. So you use another pump to push liquid through the machine. Okay, so you force a flow rate through your machine, your gear pump, and it will rotate, and you can use it as a motor. Okay, so very often, not always, but very often these pumps, the very same machine can be used both as a pump or a motor. But let's start with the pump first. So first of all, I'm sorry, H stands for useful, and this is in. Okay, so the useful power is some kind of efficiency times the inlet power. Now, with these machines, all of the losses except volumetric losses, so again, all of the losses, mechanical, hydraulic, shaft, turbulence, separation, friction, every kind of, each and every loss is concentrated into this efficiency apart from the volumetric efficiency. So HM stands for hydromechanical. So useful is efficiency times input power, and if you have a pump, then your input power is mechanical power, so torque times revolution number, while useful power is hydraulic power, so Q times delta P. And then Q is, we just developed this equation, volumetric efficiency times geometric displacement times revolution number, omega is 2 pi n, and strangely, the revolution number is killed. So at the end of the day, the pressure difference is proportional to the torque, and there are these other factors. And just for the clarity, I added here the flow rate equation again. So this is pretty much the same. What we see here is very interesting. Flow rate depends only on revolution number. Pressure difference depends only on torque. Okay, apart from the size of the machine, of course. But for example, delta P does not depend on revolution number or flow rate, and torque does not depend on neither flow rate nor revolution number. Now, if you think of a motor, you start pretty much the same. So again, this is useful. This is input. But now as you have a motor, let's think about it. The motor is something that provides me mechanical power. So now the useful power is M times omega, and the inlet power is Q times delta P, because I'm using another pump to push liquid through my pump, through my motor. Okay, so, and then again, omega is 2 pi n, and there is something tricky here. So n times Vg, revolution number times displacement, is the theoretical power, but look at this. Here I've divided by the volumetric efficiency. The reason is the following. First, think about a pump, okay? So you're running your pump at 3000 RPM, okay? And then your flow rate, your theoretical flow rate is 30 liters per minute, okay? But because of the leakage, the volumetric losses for your pump, the true flow rate is less than 30, so let's say 28. So in the case of a pump, the true flow rate is smaller than the theoretical flow rate. Everyone knows that at this point. Now let's consider the case of the motor. Let's assume that you think that if you will push 30 liters per minute through your motor, then the revolution number will be 3000 RPM. So these are the theoretical values, okay? 30 liters per minute, 3000 RPM. Now, because of the leakages, again, your true revolution number will be lower. So not 3000, let's say only 2800, okay? Again, because of the leakages, the output power, the revolution number, will be smaller than expected. Okay, so now what do you do in order to reach 3000 RPM? You have to increase the flow rate beyond 30 liters per minute. So if you have a motor, then the true flow rate requirement, the needed flow rate to reach a certain revolution number is higher than what you would have expected based on theory. Okay, so that's why we divide by the volumetric efficiency. And again, you do the maths and you see very similar equations. Delta P M Q revolution number. Good. So these are our equations. And then we might want to plot the, the performance curve. I'm sorry for the quality of the picture. So the theoretical flow rate is vertical. Okay? Why? Because the flow rate is simply revolution number times geometric displacement. The pressure does not appear. So whatever the pressure is, this is the flow rate, and for a lower flow rate, N2, you have a lower revolution number, you have a lower flow rate, okay? Now, if you take into consideration the volumetric losses, then in the case of the pump, you have slightly lower flow rates, and in the case of the motor, you have slightly higher flow rates, okay? So if you compare this performance curve to the performance curve of a standard turbo pump, then you see how different this is. This is almost vertical. This is, as we have learned, this has a declining shape. So to sum up, the flow rate is independent of the system pressure. For a motor, this means that these motors can have a constant revolution number for different shaft loads. Okay, again, so the revolution number is constant even if the shaft load changes. If you compare this against the behavior of internal combustion engines or electric motors, then everyone knows that if you increase the load for an internal combustion, so the torque basically, if you increase the torque, then the revolution number will decrease. Now this does not happen for these machines, and for a pump this means that you have constant flow rate here, constant flow rate, no matter what the pressure difference is. The consequences of this behavior will be serious, and I will speak about it next week. Okay, now let's have a look at a few of these pumps. So I'm starting with a simple double-acting piston pumps. As you can see, the piston moves back and forth. It's very important to have these valves, these check valves, to the pressure side and suction side. And you also see that as the areas are different, the delivery flow rate is slightly different. So this is flow rate versus time. Now, as you can see, this flow rate at the outlet is pulsating. In order to compensate this pulsation, which leads to a lot of vibrations, very often for axial pumps, instead of one huge piston, we use a lot of small pistons. Okay, so as you can see here, we have all these small pistons. They are moving axially. Okay, and as you can see, in this range, they are moving outwards. And when they are going to the other side, they will move backwards. Okay, so this is the suction side, and this here is the pressure side. Okay, good. So this is called an axial piston pump. This is just a standard piston pump. It just comprises, instead of one big piston, you have several small pistons, which will make your flow rate diagram much smoother and even. Okay, the last one I want to show from the piston type is called diaphragm pump. So you have a membrane, a flexible membrane that you are moving back and forth. And then you see that when it moves backwards, then this is the suction period. This valve opens, this valve closes. And when you push it backwards, then there's the delivery phase. So you have this discharge valve is open and the suction valve is closed. Now very often these are used in double layout. So here you have two membranes working in tandem. And very interestingly, they are actuated by hydraulic fluid or compressor by air. So this is very common. And these machines look like this. Okay. The main advantage of this pump is that there is no leakage. Simply no leakage at all. So if you have a liquid which is extremely expensive or highly toxic, then you want to use one of these. Okay, now for the rotary type, there are gear pumps, both external and internal gear pumps. I think the external is pretty easy to understand. So basically, this is the place where delivery happens. For the internal one, this is the place where the fluid is entrapped. And also here one. So this is a standard internal gear pair. And these are the volumes which are filled with liquid. And then it's pushed from the suction side to the pressure side. This type of pump, the internal gear pump, is used when you want to save a lot of space. So this is very compact, the size is small, and hence its power to mass ratio is very high. So that means high power in a small kilograms of mass. So for example, airplane industry loves this kind of pump. Then you can also have vane pump, which is very similar to the gear pump. You have these vanes which are moving back and forth, okay, in these slots. And just to show you that not only pumps but also compressors and blowers can be positive displacement, I'm showing you this roots blower, which is essentially, if you remember, the blower is something between a fan and a compressor. So this delivers gas. It's very similar to a gear pump, but have a look at this. It's a gear, so its rotating part is a very complex shape, and it's also three-dimensional. But this is also a positive displacement pump. Okay, so that was it about the pumps. And then in the lecture notes, please read carefully chapter 6.1 to 6.3, which explains all these things. I think it's written up in much details. And then next week we are continuing with the same kinds of pumps, and we'll put them into hydraulic systems and see how you can size such simple hydraulic systems. Thank you for your attention and have a nice week.